2. There we go. Let me reshare my screen just in case. All right. So 3.2 is pretty long. It's actually kind of cut into 2 separate pieces. So we're going to cover as much of the first piece as we can today. We might not even get to it all, but we'll try. And then the second piece, hopefully we'll get to on Thursday. So the first thing we have to talk about is something called some sequences and series. So we're going to essentially look at a better way to look at recurrence relations. So remember in 3.1 we talked about recurrence relations, which are the functions that essentially rely on themselves to find the values. So first we want to introduce the idea of a sequence. So a sequence is an ordered arrangement of numbers, figures, or objects. So unlike, say, a set, so if we had just a set of things, it doesn't have to be in a particular order, but for a sequence, it has to, like, the order that it's in is the correct order. You can't really move the elements around at all. So in 3.1, we looked at the Fibonacci sequence. That would be a sequence. You can't really move those numbers around. They have to be in that order. So since sequences are ordered, we can talk about the first term, the second term, so on and so forth, because again, you can't move them around, so they kind of have to stay in their set position. Putting you on hold? That's weird. That sounds like an internet problem. Yeah, I don't know of a fix for that. You could try going all the way out and coming all the way back in, but I don't know why it would be doing that besides your possible internet. But I put that in the chat. Hopefully something gets worked out. But I gotta keep going. So what was I saying? Sequences. Since they're ordered, we can talk about the terms in their order. So if we consider the Fibonacci sequence, the first term in the Fibonacci sequence is 1. And the fourth term in the Fibonacci sequence is 3. Sorry, I gotta move this really quick. There we go. So this essentially tells us that we could then rewrite any sequence as a function, where essentially all of the inputs are going to be positive integers. That O doesn't look like an O. Positive integers. And the outputs are going to be the terms of the sequence. So we could essentially say for the Fibonacci sequence, f of 1 is 1, f of 2 is 1, f of 2, sorry, goodness, I can't, let me back up a little bit. So for the Fibonacci sequence, we did actually define it as a function, but you can think about it like this. We could define f1 to be 1, f of 2 to also be 1, f of 3 to be 2, and so on and so forth. You know, essentially whatever the input is just that, essentially the position of the term in the sequence, and then the output is the term of the sequence. So when we write a sequence out in general, it's always going to appear as a list, and it's just separated by commas. Scroll. So if we have some a sub 1, a sub 2, a sub 3, and and we just keep going and we list it just in a list. So here, if I write it generically like this is essentially helping to show the ordering, where a sub n is, of course, then the nth term of the sequence. So often sequences are going to have some sort of pattern to them, and that's kind of what we're going to focus on, is kind of finding that pattern and being able to use it to be able to write a function. Well, obviously for this number 2 that's coming up, we won't have a function because it's dots. But as long as they're numbers, we're going to focus on trying to find a function to represent them. So let's look at these sequences and try to look at what the next term might possibly be. So we kind of want to look at, and let me kind of split this up so that the numbers of the question don't interfere with the numbers of the sequence. We kind of want to guess at what the pattern is. So say we have 1, 4, 9, 16, 25, and 36. Well, if you notice, this is 1 squared, and then 2 squared, and then 3 squared, 4 squared, and so on. So since 36 is 6 squared, the next term in this sequence is most likely 49, because that would be 7 squared. So like we kind of notice this pattern in the terms that they all end up actually being squared numbers. So we just kind of continue in that pattern. And sequences don't necessarily have to be numbers. They can be, you know, anything. So even this collection of dots can be a sequence here. So if we kind of look and see what's happening between each consecutive term, essentially we're kind of like adding on an extra piece to the end and then adding an extra row, adding on an extra piece to the end and then adding an extra row. Well, other pieces to the ends, I should say. So if we wanted to go one step up in this sequence, we would essentially need that last term. Let me kind of do that extra piece in purple just so that it's clear that this is the extra piece. And so we essentially tack on, oh, that pen is thicker. Tack on kind of an extra piece to the end and then an extra row on top. So that would be the next term in this sequence. And we could keep going in that same kind of pattern of adding on kind of an extra column and an extra row, if you will. For the third one, I got to remember to pause every once in a while to let y'all catch up. For the third one, we have 5, 8, 11, 14, and 17. So if we look at these terms and we kind of look at one compared to kind of the one directly next to it, we want to try to figure out how we get from one to the next. Well, to get from 5 to 8, we would add 3. If I want to get from 8 to 11, I would add 3. 11 to 14, I'd add 3. And 14 to 17, I'd add 3. So it looks like the pattern here is probably that we're adding 3 each time. So the next term in the sequence is most likely 20. We're not entirely sure. We're taking guesses here. Something super crazy could happen, but we're going to assume that the next is probably 20. And in this last one here, we have 4, 2, 1, 1/2, 1/4, 1/8. Well, how do I get from 4 to 2? Well, I could subtract 2, but then to get from 2 to 1, subtracting 2 doesn't work. So like sometimes you can, you know, try a bunch of different things. How else can I get from 4 to 2? Well, I could divide 2. I could divide 4 by 2. So 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4, and so on and so forth. So it looks like our rule here might be that we're dividing each term by 2. Or multiplying by 1/2 if you prefer thinking about it as multiplication. So if we think about what the next term of the sequence could be, if it continues to follow that pattern, well, 1/8 divided by 2 or multiplied by 1/2 would give us 1/16. So those are some examples of sequences and kind of how we can sometimes find a pattern in these sequences. Not all sequences have patterns. Is that a lie? That might be a lie. That might be a lie. They might all have patterns. I don't know why I'm suddenly questioning myself on that. I could just give you a, never mind. It's not always going to be easy to find the pattern, I should definitely say. That's definitely a case. That's not necessarily easy, even if there is a pattern, to be able to see it. So in these cases, they were kind of easy enough to see if we just thought about it for a little while. But anyway. So that third example that we just looked at was an example of something called an arithmetic sequence. So arithmetic sequence. And that was the one, just to remind us, this was the one that was 5, 8, 11, 14, 17, just to remind us which one I'm talking about. Essentially the one that we found that we were adding 3 each time. So in an arithmetic sequence, it doesn't quite look like an S. Successive terms, so terms that come right after another, are obtained by adding a fixed number to the previous term. This number is going to be called the common difference. And we're going to denote it with the variable d. D can be negative. So take note of that. And that would be essentially a case where you're subtracting something each term, but you would just think about it as adding a negative. Pause for a second. And then the sequence from the last one, which was the, where did it start? 4? Yeah, 4, 2, 1, 1/2, that one. So that sequence is an example of something called the geometric sequence. And in a geometric sequence, successive terms are obtained by multiplying the previous term by a fixed number, which is called the common ratio. And we're going to denote that by, we're going to denote that by r, and note that r can be a fraction. So in the one we considered, technically, I did say it as dividing by 2, but I also then reminded us that that's the same as multiplying by 1/2. So that does consider this to be a geometric sequence because we would be multiplying by 1/2. So essentially with these, you can kind of think of them as arithmetic being addition and subtraction. It's just that we'd be adding a negative, and geometric being multiplication or division. But with division, it would just be multiplying by a fraction. Well, a fraction less than 1, but. So I'll hold on for 5 more seconds in case y'all are still getting that down. So let me try to leave that in there a little bit. So we're now going to consider recurrence relations, so what we were considering in the last section. But we're also going to try to now look at the terms of these recurrence relations and try to figure out a pattern to be able to write an actual function that's not, recursive. So we're going to write out the first 5 terms, and then we're going to try to guess a non-recursive function that would essentially match that recursive relation, and then we'll use that non-recursive function to guess the 15th term of that sequence, of the recursive relation, I should say. So I'm going to scroll down past the definition of geometric sequence. Hopefully you'll have that, just so that I have more space. And I'm going to kind of break this up so that I don't run out of space. So let's find the first 5 sequences first. So 5 terms first, P of 1, P of 2, P of 3, and P of 4 and P of 5. So the first term, P of 1, is kind of our base case, the one that's defined for us, so that'll be 5. And then we'll have 3 plus 5, so 8. 3 plus 8, so 11. 3 plus 8, so 14. And 3 plus 14, so 17. So actually kind of that sequence from the first example we did. So essentially what we see here is we see that essentially the thing that's differing between each kind of consecutive term is just the plus 3. So since it's essentially differing by this just common difference, this is going to be an arithmetic sequence. So this is arithmetic with D being 3. So the common difference between each term would be a positive 3. So if you ever have an arithmetic sequence, we're going to be able to find a function that follows that sequence that's going to be linear. So this is going to gives us a linear function.
What is the n-1 for in the piecewise?
What does it say n-1 for? Is that what you said?
Yeah.
Yeah, so let me rewrite one of these in a bit more generality. So say I go back to p of 2 really quick. If I were to follow that notation as I should have, I would have done p of 1, 2 minus 1, which gives me 3 plus p of 1, 3 plus 5 from, is essentially saying that we're taking the term before it and using it to find the next term. That's what that kind of p of n-1 is telling us. I just didn't write it.
Okay, I got it. Thank you.
Yeah, I probably should have done one full out. I forgot about that. Sorry. So since we have this arithmetic sequence, if you think about a linear function and you think about the fact that a linear function has a constant slope, that's the relation between these, is that if we move over one, we go up a certain amount because it's got a constant slope. So that's kind of the link between an arithmetic sequence and a linear function. So essentially we're going to have some linear function, and what we're going to have is we're going to have that the slope of that function is going to be 3. It's going to be that common difference, whatever the common difference of your arithmetic sequence is. And then essentially what we're going to do is, so we need to find some kind of like, well, I'm going to name it Pn equals Mn plus B. So, you know, y equals Mx plus B variables in this function, in this question. So essentially what we need to find is we need to find this B value. So what we can do is we can take any one of these, you know, pairs and think of them as just a point. So like we can think about 1, 5 being a point, or 2, 8, or so on and so forth, but let's just use 1, 5. So essentially what we can do to find the linear equation is we can essentially plug in that 1 and the 5 and the 3, and then solve for that B value. So we would essentially have 5 equals 3 times 1 plus B. Subtract 3 from both sides. Well, 3 times 1 is 3. So it's just 3 plus B, subtract 3, but from, oh my goodness, my words aren't working. Well, let me write this out in full. Just in case, minus 3, minus 3. So we get that B is 2. So that would mean that we're making a guess, a very good guess, that a non-recursive function that would match this recursive relation would be 3n plus 2. The 3 coming from the common difference between the terms, and the 2 being the thing we just found using essentially one of the points we have and that common difference. And then the last thing we're asked to do in here is to take a guess using this function of what the 15th term is. Sorry, my notes have a wrong answer in them, and I just found it really funny. Oh, no, wait, they don't. I'm dumb. 45 plus 2. That is correct in my notes. I shouldn't question my arithmetic in my notes. So we would have a guess. It's technically a guess, but it's going to be the right thing. That the 15th term is most likely 47, and it is 47. The reason I'm saying guess here is because we've the function that we've found is technically a guess. What we're going to do later, probably not today, but hopefully on Thursday, we'll get to a process that we're going to use to actually prove that this function is the function that works. But up until this point, we're kind of just saying, this looks like it works, and so we're going to go ahead and say it probably does. And then eventually we'll get to the point where we actually show, yes, this is exactly the function that follows this recursive relation exactly. Anyway, questions, concerns on that one before we do the next one, which is similar, but slightly different. I'll hold on for 5 seconds. So similar idea, but now we essentially have just a different recurrence relation. So again, the first thing we're going to do is we're going to find the first 5 terms. We're going to kind of see what kind of pattern we have going on, try to figure out what type of function that might give us, and find that function. So let's find the first 5 terms. So 1, 2, 3, 4, 5. So P of 1 is essentially the thing we're given in the original statement. That's our base case of 4. And then we would have, I'll write this 1 out in generality, and then the rest of them I'll just kind of pull from, but it's the same kind of idea. And since we have these recurrence relations, they're pulling from the term before it. So I have 1/2 times essentially the term before, so 1/2 times 4 gives me 2. P of 3, 1/2 times the term before it, so times 2 gives us 1. 1/2 times the term before it, so 1 is 1/2. 1/2 times the term before, 1/2 is 1/4. So again, this is essentially that last example we did when we were just looking at the general ones. So again, if we look at kind of what's going on between consecutive terms, again, we've kind of already seen this sequence before, but if we were to look at this, we would hopefully see that each term is essentially divided by 2 or multiplied by 1/2 to get the next term. So essentially we have a geometric sequence here. Where R is going to be equal to 1/2. So remember, R is the common ratio, which we're multiplying by the terms. So you wouldn't say R equals 2 and think about it as, well, I divided by 2. It always needs to be that R is the value you multiply. So if you would divide by 2, your R has to be 1/2. Now, essentially, if we have a geometric, the type of function that's going to follow this, a type of function that essentially has each term being multiplied by something else to get the next term, this is going to give us, so it gives us an exponential function. These are the ones that look like some p equals p naught a to the t, or x or n or whatever variable. So the variable here is that exponent. So essentially we kind of have to figure that out now. So that R value, now, well, the common ratio, let me write it like this, gives us the A value in kind of this generic format that I just wrote down. So that R value of 1/2 is going to be what that A value is. So we essentially need to figure out that number in the front. What's that P naught? So what we're going to do is we're going to do a very similar thing to what we did with the linear function. We're going to take that this R is 1/2 and we're going to pull out essentially a point from kind of our first 5 terms. So since plugging in 1 gave us 4, that's essentially 1 point that we could use. So if we want to, what we could do is we could kind of plug this into the generic format. So we'll have 4 equals, I'm going to write it as P naught. Maybe I should write it as something else, but I wrote it in P naught in the original thing, so I'll leave it as that. 1/2 to the first. So the 1 goes in for the variable, the 4 goes in for the output. We don't know what that term in the front is. That's what we want to solve for. And now we go ahead and solve it. So we have 4 equals P naught times 1/2, because 1/2 to the 1 is, of course, just 1/2. To get the 1/2 over to the other side, we essentially multiply both sides by 2. So that number that we want in the front is going to be 8. So that means that our equation, the non-recursive one that's going to essentially follow this recursive relation, is going to be 8 times 1/2 to the n. So then we're asked to essentially, so maybe I should write it as P of n. P of n. We're asked to find our guess for the 15th term. Of course you don't. So this would be 8 times 1 over 32,768. Let me just see something really quick. 1 second. Oh, no, wait. I want to do this. Sorry, I'm punching things in my calculator. Which would give us 1 over 4096. Now, if you were to punch just this into your calculator, technically what it puts out is, well, mine is saying 2.44 blah, 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 blah. And then, you know, the e to the negative fourth, which essentially means the scientific notation times 10 to the negative fourth. But if I do change that into a fraction, it does give me that 1 over 4096, which is kind of a better format, but technically they would both be correct. Questions, concerns on that one? I'll wait 5 seconds. Okay. So again, with these two, I don't really want to use the word easy, but I can't think of a better way to phrase it. The pattern is easier to see than many other cases. Hopefully, that would be a semi-agreed upon statement. It was kind of easy to see that we were adding 3 and then we were dividing by 2 or multiplying by 1/2 between these terms. Again, it's not always going to be easy to see the pattern that's going on. And so what we're going to eventually lead up to is essentially we're going to be given a recurrence relation and someone's going to say, here's a function that I think works, and we're going to have to verify that it works. So that's kind of what we're going to build up to. But not quite there yet. So in example 2, the thing we just did, we found what we called closed forms. We found a closed form solutions for the given recurrence relation. Oh, it's lagging. Ooh, there we go. Closed form. So essentially these were non-recursive functions such that essentially if we're naming that function f of n, I was naming it p of n before, I probably should have used f, sorry about that. So essentially the term of the recurrence relation is going to be equal to the same term in that function. So they're going to match terms essentially. And those are really, really useful because it allowed us to find a term in the sequence without using the recurrence relation repeatedly. So we were able to essentially find the 15th term without needing to find the 14 terms before it. Keep in mind, I've kind of already mentioned that so far we've only guessed at closed forms. Closed form solutions. Up to this point, we have not proven that these are actually equivalent to the given recurrence relations. We're going to know how to do that later. Because essentially, yes, they look like they're going to match any term we can think of, but maybe the 1,000,000th term, it would be different for some strange reason. Again, in terms of the ones we just found, they would be the exact ones, but we can't say that until we know how to prove it. And so we'll find out how to prove it later. What we are going to look at first, though, is being able to find the closed form if the closed form would be a polynomial. And this is going to take a little bit of algebra. I might have to give you maybe some supplemental material for algebra reminders, depending on how much algebra you remember. But we'll see. We have a question coming up that hopefully the algebra is not too terrible. But anyway. So in the first example of the thing we just did, example 2a, the closed form was linear. So recall from algebra that a linear function is a polynomial of degree 1. And then we have a bunch of other polynomials You know, they can be degree whatever, as long as it's a positive number. Quadratics, cubics, quartics, and then they, you know, 5th degree, 6th degree, 7th degree. So some sequences are going to follow a polynomial function. And there's actually a way that we can find out if it is polynomial. Now, if it's linear, like the one we looked at, it's not too hard to see necessarily because there should be a common difference between those terms. But once we get up into looking at quadratic and cubic ones, it's going to be a lot harder to tell. So how can we tell? We'll say we're given a sequence, some a sub 1 through a sub n, and maybe it continues on. We're going to define a new sequence. So be careful. It's like this term is one thing, this is one term, this is one term. So essentially, this is going to be called the sequence of differences. Or it's sometimes going to be called the first differences. And what we're doing is we're essentially taking consecutive terms and subtracting them. And this kind of idea of taking the terms and subtracting them from each other is what's going to allow us to figure out what type of polynomial it is. So if you think of straight lines of linear functions, because they have a constant slope, this sequence, these first differences, are going to be constant if the sequence is linear, because essentially that's where you would find that common difference between all the terms. If you just subtract consecutive terms, you would get out that same value all the time. But if we essentially keep doing this, if we keep taking, so we, find the differences between the terms, and that kind of becomes a new sequence, and then we do the same thing for that, we find the differences between the differences that we just found. Sorry, I was reading ahead and I got ahead of myself. So if we kind of did that step again, where we now took this new sequence of these differences and took their differences. So if the sequence of differences turned out to be linear, which would mean that the second differences are constant, and this is hopefully going to make more sense what I mean by second differences and third differences when we do the example in a second. So if we were to take the first differences and we were to find that they were linear, or maybe we don't even recognize that they're linear, but we take the second differences, so we take the differences of the differences. If that turned out to be constant, which we're going to call the second difference, then the sequence is quadratic. Whereas if we started with a sequence, took the first differences, didn't find that they were constant, took their second differences, didn't find those to be constant, took their differences again, so that would be considered what we call the third differences, then it would be cubic. So if a sequence is cubic, the first differences are quadratic, the second are linear, and the third are constant. Now, again, we'll do an example in just one second, and hopefully that clears up what all of this means. But essentially, we're just taking all of our terms and just subtracting them consecutively, and we can essentially just continue until we hit something that's constant. And if we never get something constant, then it's probably not a polynomial. Okay, and it's essentially like, how many differences did you have to find before they were constant? If you only had to find one difference, it's going to be linear, degree 1. Did you have to take 2 differences? Then it's quadratic, degree 2, and so on and so forth. So let's see an example of that, because I know just like that might not make a lot of sense. I'll be honest. So say we want to find a closed form solution for the given recurrence relation. So again, if we were to just start listing out things here, it might be super hard to see what kind of pattern we're looking for. But let's go ahead and do that. So here we're going to say, let's plug in a bunch of n values to this thing. So let me come over here a little bit. And let me do the second one out in full generality. So p of 2 would be p of 2 minus 1 plus 3 times 2 minus 3. So p of 1 plus 6 minus 3. So 1 plus 6 minus 3. So 4. Yeah. So p of 2 would be 4. Maybe I'll do one more. and then just ask you to trust and believe me. So this will be P of 2 plus 3 times 3 minus 3. So 4 plus 9 minus 3, which will be 10. And now maybe just trust and believe me on 4 through 6. If you really want to see the worked out kind of pieces that I just wrote here for 4 through 6, let me know. But it's the same kind of idea where you're taking the term before it, then adding 3 times the number you're plugging in minus 3. So we would have 19, 31, and 46. And so here's what I mean by first differences and then eventually second differences. Is we have these terms of the sequence now. So now let's kind of we're going to take these consecutive terms and subtract them from each other. So that's why it's kind of coming out in kind of this pyramid format kind of way. So if we do 4 minus 1, we get 3. 10 minus 4, we get 6. 19 minus 10, we get 9. 31 minus 19, 12. 46 minus 31, 15. That's obviously not constant. Now, technically, if you look a bit further, you might notice that all of these values are increasing by 3. 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12, 12 plus 3 is 15. So technically, those values are linear. So we should know that since the first maybe I should avoid saying we should know. So since the first differences are linear, we could already say that it's quadratic. But again, I think the easier thing is to just keep subtracting until you get constant numbers, because it's just going to be harder to keep track of from there. So if we were to find the second difference, so what we mean by second difference is we're taking the differences of these differences we just found. So 6 minus 3 is 9 minus 6. Is 3, 12 minus 9 is 3, 15 minus 12 is 3. That's constant because they're all 3. So since we found, excuse me. So if we start looking at these kind of differences between these terms, we kind of going down the line until we get some constant numbers. And once we have that it's constant across that, whatever that difference was, so here we second differences are constant, so it's going to be a quadratic function that's going to be a closed form for that recurrence relation. So since we're quadratic, we're going to have something that looks like this, where n is essentially our variable and we don't know what a, b, and c are. Those are going to be constants, but we don't know what they are yet. But we want to find them. And we can find them by using a little bit of algebra. And again, I might need to provide some algebra reminders for us. But so let me think. So we have 3 things we don't know. We have 3 unknowns. So we need 3 functions. If we want to find the a, b, and c value, we need to have 3 equations to be able to solve for those 3 unknowns. So how we're going to find those 3 functions is we're going to essentially just take the first 3 terms of the sequence. And we're going to put them into this format of this function that we think it has to follow. Now you could take absolutely any 3 terms that you want, but it's just going to make your life way easier if you just take the first 3. So we're going to essentially say take the first 3, put them in this format, and then we're going to use those to solve. So essentially, if we plug in 1 for n, we would get a plus b plus c. And what did p1 equal? P1 equaled 1. So all of that would have to be equal to. If we replace n with 2, we're going to get 4a plus 2b plus c. And what was p of 2? P of 2 was 4, so all of that will be equal to 4. And what if I replace n with 3? We'll have 9a plus 3b plus c. And what was P of 3? That was 10. So this whole equation needs to be equal to 10. The reason we're setting those equal to those values is because we want the non-recursive function that matches. So we need to match up. Plugging in, 1 has to give us 1. Plugging in 2 has to give us 4. Plugging in 3 has to give us 10, or else it's not going to match. Hopefully that made sense. So now we need to do lots of algebra to solve for A, B, and C. So way back when, in algebra class, there were a couple ways to do this. Now, since we have 3 unknowns, it kind of makes our life the tiniest bit trickier. But we have this super nice one that we're going to be able to use to help us out here. So we're going to use something, let me kind of remind us of the name. We're going to use elimination, is what this is called in algebra. And it's solving a system of equations. If you're trying to look stuff up later because you had no idea what the heck I was doing. So essentially what we want to do is we want to essentially take 2 of these kind of equations that we have, and we want to manipulate one or both of them such that when I subtract one from the other, I get rid of one of those variables. So look at this. Let me take this second equation. Let me just try to use colors to make sure we really see what I'm doing here. Now again, we have this really nice function, this a plus b plus c equals 1. That's going to make our life a lot easier. So let's just say a plus b plus c equals 1. Do I want to follow my notes or do I want to do something else? You know what? No, I want to follow my notes because you might not always have that very nice function. Whoops. So, or do I? Oh, just, okay, nope, I'm gonna just do it. So there's a couple different ways you can go from here. So that's why I'm kind of going back and forth. Do I want to follow my notes? Do I not want to follow my notes? I'm going to follow my notes because while there's a different way we could do it here, it's not always going to work. So I'm going to show you the way that, kind of always works. So say I want to get rid of this A term. Say I want to make them disappear. So what I would have to do is I would have to take this second equation and essentially multiply it by 4 and then subtract the 2 equations. Because if I were to multiply that equation by 4, I would have 4a in the beginning, and 4a minus 4a would cancel out and give me nothing. Okay. So if I were to multiply that second equation by 4, and then I'm going to subtract the 2 things. So if I have 4a minus 4a, that's going to, cancel each other out. I'm going to write 0 just to remind us that that canceled each other out. We're going to have essentially, so let me go even a bit further and do 4a minus 4a so that we know where that came from. I don't know how much algebra y'all remember, so I'm just trying to do it super in depth. Then we'll have essentially 2b minus 4b, because that 4 goes to each one of those terms. So that'll give us minus 2b. And then we'll have c minus 4c, so minus 3c, and equals 4 minus 4, so 0. Again, there was a bunch of different ways we could have gone with this one. If we had just subtracted those 2 equations, we would have gotten rid of c. But again, sometimes you don't have that process where things just automatically cancel out. Sometimes you will have to use this process of multiplying one of the functions by something else to be able to get things to cancel out. So that's why I'm going to continue on in this way. Anyway, if what I just said doesn't make any sense, forget it. So essentially what I have now is I have minus 2b minus 3c equals 0. Let me just clean it up a little bit, and I'm going to box it so that I remember that I can use that later. So notice that now I don't have 3 unknowns, I only have 2 unknowns in that one. But if I have two unknowns, I need two equations. So now I need to manipulate essentially another pair of the equations that I have to do the same kind of thing to get down to another something that looks like this. Hopefully this is making sense. So let me pull that third equation and the first equation again. Now, the thing is, once you kind of choose a path, you're then kind of forced for the second thing. So the first thing that I did was I chose to eliminate that A value. So now I still have to eliminate my A value, or else I'm going to get out to something that's not helpful. So I need to eliminate my A value again. So what I would need is I would need to essentially subtract that second equation multiplied by 9, because I need to cancel out this 9A, so I'd have to build it up to a 9A. So we get 0. I'll do this one out in full generality, 9A minus 9A. 3B minus 9A would give us negative 6B. C minus 9C would give us negative 8C equals 10 minus 9 is 1. So our second equation that we get from this way is negative 6B minus 8C equals 1. These questions have a lot of work to them. Because what we need to do now is we need to take those two equations and essentially use them together to then cancel out either B or C to then solve for the remaining variable. So let's kind of write these on top of each other. I'm going to write the one with the larger values on top. That's just personal preference. You can do whatever order you want. So let me try to figure out how I could manipulate that second equation such that when I subtract the two, I would cancel out one of these terms. Well, notice that I have an 8 and a 3 on the C's, and there's no super nice way to build a 3 up to an 8 with multiplication. So that's probably not the best way to go. But I can build up a 2 into a 6 with multiplication if I multiply by 3. So if I multiply that second equation by 3, that's going to cancel out my B's. Because we'll have negative 6B plus 6B gives us 0, which is what we wanted. And then we'll have negative 8C plus 9C, so just C. And then 1 minus 0 still, because 0 times anything is still 0, so 1. So ta-da! C equals 1. Let me box that too. Hooray! We found one of the 3 variables that we needed. But once you've found one, it gets easier. We've done the bulk of the nasty algebra work. Because essentially now what you can do is you can take that C value and you can plug it in to whichever one of these two equations make you happier. Let me just clean that up a little bit. So we're going to plug in C to whichever one makes you happier. They should give you the same value. Maybe if you want to triple check your work, you can plug it into both, because if they don't give you the same number, something went terribly wrong. So let's say I want to plug it into the negative 2B one. Whoop. So I'd have negative 2B minus 3 times 1 equals 0. So negative 2B minus 3 equals 0. Negative 2B equals 3. Maybe I should have been taking a lot more breathers here. I'm really sorry. I'm still not used to teaching to a screen. So we'd get negative 3 halves. I'm going to pause for a second. Are there any questions? So I'm really sorry. I should have asked that already. Wait like 5 seconds. Okay. So now we've found the second value that we needed. So now we plug in B and C into essentially whichever one of these equations makes us happier. I would say plug it into A plus B plus C equals 1, because you don't have to multiply things by anything. But that's just my own personal preference. So I'm going to take the A plus B plus C equals 1. And I plugged in the values as I was saying B and C. So we have A. I would actually have done it like this. I would subtract 1 because that'll give me 0, and instead of having to add the negative 3/2 to 1. But as long as you do the algebra right, it shouldn't matter. So we get A is positive 3/2. We've found all 3 of our pieces. So now triumphantly, after all of that obnoxious algebra, we have now found a closed form for that recursive relation. So it was in a generic format, an squared plus bn plus c. So now that we found all of those values, you have 3/2 n squared. I guess minus 3/2 is how I would write it. Minus 3/2 times n plus 1. Whew. So this function would give us the exact same terms. I'm going to scroll up really quick. I'll scroll right back down in a second. As the original recurrence relation that we started with. So just to recap, I'll scroll down as I recap. We found our common differences, not our common differences. We found our first and second differences. We found that the second differences were constant, which meant that this must follow a quadratic form. We kind of wrote out a generic quadratic form. We plugged in the first 3 terms. We got 3 generic equations. We did lots of algebra to be able to solve for all of our things. We had to eliminate one of the variables in each case for 2 sets, find 2 different equations, essentially eliminate one more from them. We found C. Once we find one of them, we're kind of home free because then we just got to plug them in. So we plug them into the equations that we had before and solve for the remaining variables, and then just push it all together. Whew. That was a long one. Questions, concerns on that? I'll wait like 10 seconds so your brain can get up.
Are you going to show a cubic example or no?
I don't have one in my notes.
Okay, I just had like one question about it. Is like for the elimination, is it going to change with a cubic function?
So the only thing that would change is that there would be more steps. So essentially, with a cubic, I'd probably never give you a cubic question, but essentially a cubic would end up, because you'd have an an cubed plus bn squared plus cn plus d, so you'd have 4 unknowns. So you'd have to start with 4 equations, and so you'd have to start with 4 equations, do an elimination to get 2 that have, no, you'd have to do an elimination 3 times to get 3 equations that have 3 variables, and then do elimination. So essentially, you'd have to take, equation, subtract the 2, get some equation in 3 variables. Equation, get some in 3 variables. Equation, get some in 3 variables. And then once you found those 3, you would start this. So it just kind of keeps building upwards the more variables you have, the more unknowns you have. It's the same type of process, you just have to do it a lot more times. I don't think I will ever give you a cubic because I wouldn't want to do a cubic myself, but that's how it would work. In general, if like people were doing these, I honestly don't know what job would actually care about finding these, but say you wanted to find these and you were trying to do these fast, we would have to pull out these things called matrices. I don't know if any of you have seen matrices before in your life. Matrices are a kind of quick way to solve these, and you would probably just plug it into a computer and tell the computer to solve the matrices for you, instead of having to do all this obnoxious work. But we don't do matrices, so we can't use them. But to answer your question, it's the same thing, just with a ton more steps. But you'll never have to do a cubic. Because I wouldn't want to do a cubic. But hopefully that answered your question. Any more questions? All right. Oh crap, give me 1 second. Oh no. Oh, okay, I see. Okay. Yeah, I don't think I'd ever give you a cubic. Anyway. So if we're okay with that, I know it was a lot of algebra. And again, if what I did was, you know, Greek to you, try to look up some elimination, solving a system of equations with elimination. That's essentially what this process is. It's an algebraic thing that I'm supposed to be able to assume you know, but I know that it's not something that's brought up every once in a while, so you might be super rusty on it. Last 15-ish minutes. Let's go ahead and define a couple more things. We could possibly get at the end of this section. I don't know. But anyway. So back in 3.1, you don't really need to recall it super well, but we looked at a sequence that was this. It was essentially that idea of, you know, you worked one day, you got a penny, and then every day afterwards you got double the amount of how much you had before. So we eventually ended up with essentially this sequence here, where the nth term was represented by twice the amount you had the day before, and it was that day's amount. So what if you wanted to know the total amount you've earned in working some amount of days? So what we would essentially do is we would, of course, add all of those wages together for those days that you were working over. You would just add them all together. So say we wanted to figure out how much pay did we get for the first 5 days. We would take the pay in the first day plus pay in the second day plus the pay in the third day and the fourth day and the fifth day. Add them all up. You get 31 cents. Whoop, whoop. But, and obviously you could continue doing this for absolutely however many values you wanted. So notice that kind of comparing this to the sequences we just looked at is kind of similar, except now our commas are plus signs because we're adding the terms instead of just listing them. But this idea actually gives us a new type of thing. So we can essentially take a sequence, and if we were to add up the terms of a sequence, and even just the subset of the terms of a sequence, we kind of get this new thing. This new thing is called a series. So a series is a sum of the terms in a sequence. We're going to use something called sigma notation. You may have seen before in your life, to be able to write these super compactly. So essentially say I have some a sub 1 plus a sub 2 plus blah, 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 all the way up to a sub n. We can write that in sigma notation. So we have this big sigma, which is why it's called sigma notation. And so if you notice, all of these terms have like a common layout to them. I could say a sub I. And essentially those I values start at, if I were to replace that I with a number, I essentially start at 1 and I go all the way up to n. So essentially that sum of a sub 1 all the way up through a sub n can be written as kind of sigma from y equals 1 to n of a sub I. So we essentially take the generic format of all of the terms. So in this case, with the series, they should have some kind of pattern to them. They should have some kind of generic format that they follow. So we should be able to find the generic format of them to be able to write them in the sigma notation. So expand and evaluate the sum given in sigma notation. So now we have something in sigma notation and I kind of want to expand it out into its full sum. So all of the terms are going to look like 2 times something, and the something is going to start at 1 and it's going to go up to 5. Another thing that I kind of slipped through the cracks here, these numbers are only integers. You're not plugging in, 1.5, you're not plugging in 2.2. It's just, If you start at 1 and you go to 5, it's 1, 2, 3, 4, 5. It's nothing funky. So essentially this would look like 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 5. I plug in a number everywhere I see an I, and those numbers start at 1, and I stop when I hit 5. If you care, that comes out to be 30. So say instead I wanted to go backwards. So I have this sum. I have 1 plus 4 plus 9 plus 16 plus 25 plus 36. And I want to write it in sigma notation. Well, I need to know kind of the pattern of those numbers. What's the generic format of those numbers? So if you look at these numbers, we've kind of looked at these numbers before. So we have 1, 4, 9, 16, 25, and 36. Those are all squares. We have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So if I think about it, kind of that generic format that they follow is they're all some I squared. I is just usually the letter we use. Some people use J, some people use K. It can kind of be whatever letter you want it to be. I, J, and K are usually the typical ones. But anyway, so they all look like some I squared. And where did my sum start at? What was the first I value I used? It was 1. What was the last value I used? It was 6. So that's how we would write that in sigma notation. Now note that sigma notation, it can be written in a ton of different ways. We're gonna, kind of do the one that's the simplest. Like if I really wanted to be a jerk, I could technically say, well, this is some I minus I plus 1 squared where I starts at 0 and ends at 5. Like technically that gives me the same thing, and I could just keep being a jerk and keep adding numbers or subtracting numbers and just changing my little indexes. Indexes are the words for the top and the bottom thing. But we're kind of always going to just go to the simplest one and try to not be a jerk about it. But technically, in general, sigma notation can kind of take a bunch of different forms. Anyway. So I'll hold on for 5 seconds just in case. Okay. So notice that these series can actually be thought of recursively as well. So say I have some very generic, sum of things. So, this would be a sub 1 plus a sub 2 plus a sub 3 plus blah, 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 plus a sub n minus 1 plus a sub n. If you notice this, everything except that last term would be essentially, why am I using k all of a sudden? Would essentially also be a sigma notation just to k minus 1, n minus 1 instead of n. So I could also think of this as sigma notation for I equals 1 to n minus 1 of a sub I. Kind of have to tuck that in parentheses so I know that that's the end of my sigma notation. And then I could just add on that last term. And I could keep breaking it up, and that's why we could eventually define it recursively, because we could jump all the way down to the first term, a sub 1, sorry, and build up from there. So it does kind of also have kind of this recursive format. That's just kind of an interesting note. Might not be interesting to you, but it's a note. We've got 10 minutes. So actually, we can finish this one, which is good because that's good. So say I want to do this. Without a calculator, add the first 100 positive integers. Now, there's a few different ways you could go about this. You might have seen this done before in your life. I'm going to go a very specific route because of what I want to write generically afterwards. So essentially what I would love to do is I would love to add all of these numbers, and I want to go all the way up to 100. And I want to add all those numbers together. Well, let me do a kind of strategic thing. And let me repeat that but backwards. And let me think about kind of adding these two groups together. And again, I'm doing this in a very specific route. There's a couple different ways you can kind of finagle this. If you think about adding all these together, 1 plus 100 gives us 101. 2 plus 99 gives us 101. 3 plus 98 gives us 101. 4 plus 97 gives us 101. And that's not a coincidence. That's going to continue onward. 99 plus 2 is going to give us 101. 100 plus 1 is going to give us 101. How the heck did that help us? Well, if we notice, all of those are 101, which is kind of the point. We kind of now have created something that's the same everywhere. If you think about how many of these we have 100 terms. Because we're adding 1 through 100, and we took that 100 terms and essentially added it to itself, but backwards. So we have essentially 100 101s. So you can think about this as being equivalent to 100 times 101. Right? If you have 100 things and they're all the same thing, that would be 100, the amount of terms you have, times 101, what all of those terms were. But remember, this is twice what we want, because we added the first 100 integers to themselves. So now we essentially have 2 sets of the first 100 positive integers. But that would mean that the sum of the first 100 integers, written in sigma notation, would be equal to this 100 times 101 divided by 2. Just cut it in half. Which, if you're curious, would be 50-50. So again, for the first 100 integers, there's sometimes people will break it up at 50 and add the 1 to 50. Yeah, and then 51. They'll have 50 terms of 51. But the reason I did it like this, and I kind of did it out in full generality, is because we can essentially do this for any integers. So one thing that's kind of an important thing to note, I don't think you have to commit it to memory, but I'll triple check that. Again, this is my first time teaching this class, so sometimes I don't realize what you need to have in your brain, what you don't. I don't think this is something you'll need to commit to memory. But essentially, no matter what n is, if we want to find the sum of the first n positive integers, we can kind of use that similar format where we could take the, series that we want, add it to itself, and then have kind of this multiplication fall out from it, and then just take that value and divide it by 2. So that's just kind of a cool tidbit. But that's the end of the first part of 3.2 notes. Again, 3.2 kind of comes in 2 parts, and we'll look at the second part on Thursday. What do I want your quiz to be on? That's a good question. Well, no one asked, but it's a good question that I asked myself. Let me think. So what have we done? We just had one on graphs. So it'll be on 3.1, and I could put 3.2 on there. So what do I want to do? Let's see. Quiz on Thursday. I'll answer that in one question. 1 minute, Sam. My brains can't think of 2 things at once. So from 3.1, what you want to focus on for the quiz is recurrence relations. And what I mean by that is finding terms. So say I give you a recurrence relation, then say find the 6th term or something like that. Find that term. Let's see. That's probably the only thing I would ask you from 3.1. So then from the stuff we went over today, I might ask you to find a non-recursive function that matches. And specifically for the quiz, not necessarily for the exam, but for the quiz, I'm just going to do linear or exponential. kind of, if I scroll back up, up. So what I mean, and I'm typing this in chat, so it'll pop up in a second. So on the quiz, you won't have something like this where it was quadratic. On the exam, you might, but on the quiz, no. But I could ask you, come on, keep going. One like this that we did kind of towards the beginning, where it was, I gave you the recurrence relation and asked you to find the function that matches. So it'll either be linear or exponential. I won't go any further than that. So that's up in chat. So recurrence relations from 3.1, finding terms, and then 3.2, kind of, again, this idea that I just scrolled up on the screen for. The exam is next Thursday on the 22nd. And Sam asked, is there any formulas or definitions that will be provided like last exam or no? Sorry, but no. So the last exam, I provided those inference rules because I wasn't going to require you to memorize them. There will not be a formula sheet for this one. As I'm told, most of the other classes only have that for first exam. So I'm kind of following how the other professor is doing his, and since he doesn't give any others for anything else, I'm following his lead. So yeah. So a couple minutes early, but not worth moving on. So if you have any questions, feel free to stick around. Otherwise, have a good day, and I'll see you on Thursday. Let me stop the recording.